technologies to supply the demand with 100% renewables. So to dive straight in, we're going to look at this notebook for today. And if you think back to last week's lecture about optimization, kind of this is the software mapping to that lecture. It's a framework for formulating optimization problems, interfacing with the different solvers. There's separate software that solves your optimization problems, applies these different algorithms like the simplex algorithm or interior point algorithm in a well-defined task, and then communicates the optimized results, the optimized outcomes back to a software tool like this, for example, in a specified data format. And often there's just an abstraction layer between the real application models like PipeSA, for example, where it's kind of about optimization in power systems, and the solvers itself, so that you have just one way of formulating optimization problems in a specified format, so that you can also quickly exchange between solvers. So it might be the case that sometimes you maybe have an easy problem, so that can still be solved with open source solvers. And sometimes you have really hard problems that you can only solve with commercial software. Then you don't really want to rewrite all your models so that it can communicate with a different solver, but you want kind of an abstraction layer in between. And this is what linopy does. It was also originally developed in our group by one of the postdocs in our group. But there's a range of different frameworks for working with optimization problems in Python. One other popular one, there's also an introduction for that as additional resource, is Pyomo. And there's also Pulp, for example, and there are various solver-specific interfaces as well in Python. The reason why we're going with linopy in this course is that PipeSA itself, it uses linopy in the backend now. And the original reason why we developed linopy was that we needed something that was really performant for large-scale problems, which Pyomo couldn't offer at that point. So linopy is kind of a framework that's specialized for the type of models that we're solving in the energy world, and supports just a kind of reduced set of optimization problems compared to Pyomo, but does that maybe a bit more resource efficiently. So if you think back to the optimization lecture, you had these different components, like formulating an objective function. What are you optimizing for? Your decision variables, the unknowns, the kind of things that you want to have answers to, how much capacities to build, how to operate the storage, how to operate a conventional power plant, for example, and then these various constraints like adhering to the capacity limits as well as the energy balances, Kirchhoff laws, and so on and so forth. So linopy will give you kind of structure to formulate all these essential elements of an optimization model, communicating with the solver, and then also retrieving the results. The specific classes that linopy supports is linear programming, so everything is linear. All the objectives, all the constraints are linear, and the variables can take continuous values. But in principle, there's also options for integer programming, so where your decision variables are kind of yes or no decisions, or 1, 2, 3, 4, 5 decisions, but not 1.5 decisions. Mixed integer programming, where you mix the two, and also it has an interface for quadratic programming, where you maybe have a quadratic term in the objective function. But what you see in bold is what we're going to do in the course. It's a bit simpler to learn, and now I'm going to switch over to the interactive version. And it basically follows all the things that you already know from all the other Python packages, that you start with usually you would start with some basic class, a model, an object, where you put everything else. And in linopy, it's the model class for optimization model. And what we want to do in this first example is we want to rebuild this simple optimization problem. So it's not very complicated. It doesn't have any indices, for example. It's just just has two variables, x and y. There's an objective function here, and then a couple of linear constraints around that. So what do? We import linopy, and then we initialize a model object. It's kind of handy to have a very short variable name for that because we're going to reuse that quite often. And then we initialize the model, and that's going to give us an empty model. And then we go through the different steps, step by step, to add the essential components of an optimization problem, usually starting with the decision variables, and then we basically have the choice whether we want to start with the constraints or start with the objective. The unknowns of this example are x and y. So we have here this function add variables, where we give the variable a name. In this case, we can give it the name x. The second variable gets the name y. And we can also set already some lower and upper bounds. So some very simplistic constraints that just depend on the variable itself and not on combinations with other variables. So these two constraints here, x bigger than 0, y bigger than 0, can set directly when initializing the variables. We get these objects returned as x and y. We can look at x and we can look at x, for example, and it will just give us some representation of, here we have this variable x, and it can be in 0 to infinity because we didn't set an upper bound, so the infinity is kind of implied here, and we have the same for y. If we want to get an overview of all the variables in the model, you can just go with m.variables. It will tell you, here we have variables x and y, and we can then also, in principle, access the variables from there. So if we, for example, didn't store x and y as separate objects, we could still access them from here. Pretty much the same we can do for constraints. Constraints, you have basically three elements: your decision variables, the coefficients associated with the elements, and the linear combinations of those two are typically referred to as the left-hand side. And then you have right-hand side, some constant, some limit. For example, 10 here in this case. So we're just re-implementing one of the constraints from the top. I'm not going to scroll up to show that again, but it's just we say 3 times x plus 7 times y must be bigger than or equal to 10. And that will then give us just a constrained object that we still have to add to the model. As you see in this command here, we don't have any reference to the model object. So we have a free floating constraint that we now need to attach to the model. Let me just... And that would be kind of the other constraint, well, a similar constraint where we could also just write the right-hand side. We don't have to do it. linopy will automatically kind of rearrange it so that the constant terms will end up on the right-hand side. And so we can now take these constraints. This is one, and this would be the other, and add them to the model with the add constraints function. And when we do that and run m.constraints, we would see what the constraints are. Here we have we didn't give the constraints any names. So linopy will just start counting from 0, con 0 and con 1, and these can be accessed. And I think we could just add a name here, for example, if we wanted to. So we have constraints, variables. What's missing is the objective. And there's, of course, also a function add objective. And in principle, and the principle is just the same. You form your expression. So x plus 2 times y. It's pretty much Pythonic syntax here. And you provide the optimization sense. So we have this function. Do we want to minimize it, or do we want to maximize it? And that we can then also just look at. Here we get the linear expression, the sense, and once we have solved the model, we will also get a value. And at this stage, it's none because it's not a solved model yet. So if we want to get a summary of the model, we get a list of variables, constraints, and yeah, not the objective, but at least we say, okay, the status here is initialized, and that means we can solve it. So there's just an m.solve function. And that is now the point where this could look differently depending on what solver you're using. And everything I see here, apart from this return statement, OK optimal, which is linopy's way of saying, okay, this model was feasible, it could be solved, the constraints didn't contradict each other, and there's not a kind of infinite solution, for example. But all the rest here is logging from the specific solver. In this case, Hi is one of the open source solver variants, solvers. And it can be a bit cryptic if you didn't take too many optimization courses yet, but maybe I'll walk you through some bits of it, but not all of them. So what you see here at the beginning, you see the specific version of the solver to be run. You see here how the characteristics of your optimization problem. So here we have 2 rows, 2 constraints, 2 columns, means 2 variables, and then 4 non-zeros, which means we have 4 coefficients in all of the constraints that are not 0. Because we have in the constraints here, we have 2 constraints, and in both constraints, we have both variables involved, 1, 2, 3, 4 non-zeros. So this can help you sometimes to find out if something is wrong with your model, if it's scaled badly, for example, if it's badly conditioned. And also these coefficient ranges here, kind of the value ranges of your right-hand side of the constraint, of your matrix values of the coefficients, the variable, kind of the left-hand sides of the constraints, and your variable bounds, as well as your the coefficients in the objective. You get some statistics here. The second stage here that you typically will see is the pre-solving part. So this is a stage where the solver tries to kind of reduce redundancies in your model formulation. And then it will hand it over to one of the solver algorithms. So remember, I mentioned last week interior point barrier algorithm as one option and simplex as the other. And typically the solvers, if you don't specify anything, they will go with one standard that seems suitable for the model at hand. And then at the end, you will get something like what is your error? So what are your tolerances, basically? How close did you get to the optimum and the optimal objective value? And in in more complicated problems, you will see just what the runtime is. And I'm not sure what other solvers I have installed at the moment. Let's see. But if Ruby not is installed, maybe this one is installed or this one is installed. No. So in principle, the logs would just look a bit different for the different solvers. Here's a list you can go through, things you can try out. I think so. Apparently, in the course environment, we only have Highs installed. Okay, so now we already have done. Yeah, there's a question. Yeah.
That there is no tolerance. How can I link the tolerance that I already have to the model or to the linopy?
Yes. So in principle, the first thing that you need, and that is true for open source solvers as well as for commercial solvers, is that you have the Python package installed. And I'm pretty sure in the course environment, there's Highs already pre-installed, but it can also be installed with conda install HiSpy, for example, or pip install HiSpy. And once that's in the environment, it should be automatically linked. And for the commercial solvers, it's because they need to do some form of check whether you have the right to run this code and use this, you will have something like license files or kind of passwords, passkeys that identify you and allow you to run the software. And that's typically file-based, where you have to put a license file somewhere on your computer bit. So, yeah. The license file doesn't need to be linked with linopy. It's automatically linked when you have the Python packages for the solver installed. So like for HiSpy, there's also a Gurobi py, for example, if you want to use Gurobi, and then it's automatically linked. Yeah. Okay, so we've done 2 steps already. We've formulated our first optimization model. We've solved it with one of the open source solvers. And now we also want to retrieve what actually was the solution. And for that, there's the solution attribute in linopy, which returns an X-array dataset. So X-array you already know from AdLight. It's just a multidimensional way of pandas. Or it's not really a derivative, completely different backend, but the idea is that you have tabular data, you have n-dimensional data, and have some data structure for that, an array. And here we see, because it's easy now because we only have scalar values. So the optimal value for x would be this one, and for y would be this one, 1.41. We can also read out the objective value. So what was the optimal objective at the optimal solution? And this would be 2.86. Remember in the last lecture, I also mentioned that there's actually something more that we're interested in than just the objective value and the optimal values of the decision variables. We can also learn something about the sensitivity of the objective function to the different constraints. So what happens if we change our constraint boundaries a bit? How does our objective value react to it? These dual values, or sometimes shadow prices, because they tell you what would happen at the margin if you relaxed your constraint by one marginal amount. How much would your objective value change? So these dual values, they will always have in units the unit of the objective function divided by the unit of the constraints. So for example, we could read out the dual of constraint 0. And this 0.27 would mean for if I add one incremental amount of slack, be less strict about the constraint con 0, by how much our constraint our objective value would change. Okay, so that's all we need to do in principle, but we can of course add a little bit more complication to that. For example, adding indices and dimensions to the decision variables, but in principle, the core principles we have covered now. So coordinates in linopy are basically indices that you know from the way we talked about optimization models last week. So we have kind of coordinates for NumPy arrays, for example. We have kind of positions 0, 10 gives us the first row, the 11th column, for example. And the same, we basically have the index and the columns in pandas data frames. And suppose we now have this model where we have this slightly modified problem where we have an additional index t that lives in both x and y. And these constraints here, they then are kind of duplicated for each of the t's. And the right-hand side here just depends on the t. So if you have t10, your right-hand side would be 100. If you have t9, your right-hand side would be 90. So let's start with a fresh linopy model. And what we can do now is we can use pandas to write up a time index. So just an index that goes from 0 to 9, I think. So 10 values. And now we can add variables in a slightly modified way. We still have the name that we give to it, the lower range that we give to it, but now we also pass some coordinates. And here we only have, and we would pass them as a list. And here we only have kind of one index level, so we only pass our pandas index time in there. And we do exactly the same for y. So if we now look at x, for example, instead of just one scalar value, we get the 10 x values with their corresponding indices, and we also get the size of the different dimensions displayed here. So for the constraints, we can basically construct a pandas series of factors. That would just have the t index as the index, and then the factor, the actual value, as values, so that we can say we have 3x plus 7y must be bigger than or equal to 10 times the time step. So that would give us exactly the constraint we want, that kind of with growing time index t, we have a growing right-hand side. And that we would just add, like before, to the model with the add constraints function. That's exactly the same. For the objective, what we can do is we can basically use similar syntax to what we're used to with pandas. We can say we want, let me just extract that. So we can say x plus 2 times y would give us linear expressions, which is indexed with our time index. But what we want is that we actually want to sum we want to sum across the time dimension. So we can just say sum, and what we would get out of that is just we kind of sum up all the rows in the previous expression. And that we can use just as an objective. So just to check briefly what our m.objective looks like, we want to minimize the sum of x and y with the corresponding coefficients. Now we can solve it again. It's exactly the same, still easy, still fast to solve. Objective value is 128. And we can now get the solutions. So still it's a kind of this x-array object, but if it's kind of 2 or 1 dimension, it's probably easier to look at it as a data frame, and there's a 2 data frame function that you can use. So now we basically just have, for the variables x and y, we have the optimal values for each of the time indices. And that we could, in principle, also just plot. So this is exactly the same as before. And then this is a pandas data frame, so we can do all the things that we like about pandas data frames, such as plotting that. Good. So these were 2 optimization model examples that are completely unrelated to energy. So let's do one example that looks at energy systems. Still quite easy. We're starting with a single bidding zone, so single market region, and a single period. So that means also no storages involved. And we're going to look at a short-term perspective like we have last week, where we just want to, that's maybe not rendered nicely. So maybe I'll just go here. What do we want to do? We want to minimize our operational cost. Our OS is the kind of per unit cost, per unit of energy generated, and then our GS are the decision variables of how much the different power plants dispatch. And then we have the constraints that the power plants need to remain within the limit and must be positive, and that the sum of all the generators must meet the demand. And we're going to use a data for stylized South African electricity system, where we first of all collect all the different input parameters of the optimization model, such as the marginal cost, so that would be the OS, where we have for wind, coal, gas, and oil these costs, 0, 30, 60, and 80. These are costs, I believe, are already in euros per megawatt hour electricity. What else do we need? We need the capital Gs, the capacities of the power plants in megawatts. So we have 3 gigawatts of wind, 35 gigawatts of coal, 8 gigawatts of gas, and 2 gigawatts of oil. Also as a Panda series here. And then we say that we have a perfectly inelastic demand of 42 gigawatts that we want to meet. And again, we're going to start just a simple model, starting with the variables. And here it's easy to directly specify the lower and upper bounds of the generators, so we don't have to write them extra as constraints. We can just say we want to add variables that are between 0 and the respective capacities, where the index, the coordinates, are just the index of our capacities data frame, and we name this variable G. So what we have now here, we have the different wind generators, the different generators in different categories, and their corresponding limits. Then we can continue with the objective costs, where we just say our marginal cost values times G would give us this linear expression of kind of, 4 different elements. And in principle, to build one term, we would also just say dot sum, so that would just give us our objective term. This is one step that we can skip. If we pass kind of just this list of expressions here to add objective, it will automatically sum them all up together. But if you want to have, if you want to write it up completely, then you could also just say you want the sum of all of that. And then your objective looks like that. Seems to be all good. And then we only have one constraint that we need to take care of, that the kind of sum of the generation. So this term will just be a linear expression of all the generators, each contributing equally, because the G represents the power they produce. Must be equal to the load. We can name it, for example, energy balance. And then we can solve the model, get an objective value out of that, get the optimal dispatch of the different power plants, as well as the market clearing price, which we can read out from the dual of the energy balance constraint. So what we have here is the market clearing price would be 60 euros per megawatt hour. And why is it 60 euros per megawatt hour? Is because the gas with the cost of 60 euros per megawatt hour, it would be the one that would supply the next unit of demand. We have wind that had lower marginal cost, which runs at capacity. We have coal, which is lower marginal cost, runs at capacity. And then we have oil, which is like really high marginal cost, so it doesn't run at all. And then we have gas, which runs at partial load. And if you have a single bidding zone, and then the generator that runs at partial cost, at partial output, so it doesn't run it runs, but it doesn't run at capacity, is your indicator for being a price setting generator. So the 60 that we see here directly translates to the marginal cost of the gas generator. So how would this look like if we add a spatial dimension here? If we add another bidding zone with transmission connected between them, so we have now a bit more constraints that we need to take care of, including basically the energy balance becomes Kirchhoff current law because we take care of the incoming and outcoming flows using the incidence matrix. And if we And in this example, we're going to only connect 2 bidding zones. So there will be not really a cycle in the network. So we can, for now, forget about Kirchhoff voltage law. But as soon as you would have 3 nodes connected with each other with 3 lines, you would have a cycle. So you would have to also take care of this constraint. So what this example does is we have the same South African system, but now we're going to connect it to some hydro generation unit in Mozambique through a single transmission line. Again, we're going to just construct us our input data. So we have coal, wind, gas, oil, and now hydro as well, and as countries. So this will be another index. We have South Africa and Mozambique. And the capacities we construct us as a data frame so that we have kind of as index the countries, as columns the generators. And you can do it in different ways, but in this case, we'll just put kind of for the capacities that the corresponding other country doesn't have, we'll just put a 0. It's not the most efficient way of doing it for large models, but these are small enough to do that. And then our variable costs, they don't depend on the country. So we'll just keep them as a Panda series. And the load also becomes a Panda series now because we have the countries as an index. And our transmission is actually scalar because we only have one transmission line in this network. So let's start with an empty model. And for the G, we basically can now take again, as lower bounds are 0, and as upper bounds, we can pass the capacities. Note that here, we don't really specify the chords. And we can do that in the add variables function because linopy tries to infer the coordinates from the upper or lower limits that we give it. So here from the data frame, it's quite clear what the dimensions should be. Well, one of the dimensions should be the countries, and the other dimension should be the generators. So if we do that and look at G, we see that the dimensions have been automatically assigned. We have 2 countries, 5 different types of generators, and some of these dispatch variables are automatically constrained to 0 because the only generator in Mozambique in this example is the hydro, and then South Africa doesn't have a hydro. Yeah, everything else is basically the same, only that we have 2 indices now. We'll now have also one additional decision variable, and that is the flow between the 2 countries. And we will orient our flow in a way that it is positive if the flow is from Mozambique to South Africa. But in principle, it can go both directions. So it goes from minus 500 to 500, and 500 would mean flow from Mozambique to South Africa, and minus 500 would mean flow of 500 from South Africa to Mozambique. So this we have to encode now in our energy balance, where if you look at the perspective of South Africa, if you look at the nodal balance of South Africa, then a positive value for the flow would look like a generator. It should have the same sign as a generator. If you look at it from the perspective of Mozambique, any positive flow here would be outgoing, so it will have the same direction as a load. So we have to be careful here about the orientation of this flow variable. It doesn't, okay, I already executed that. We have to be careful about how it is arbitrary. We could define it exactly the other way around. That would mean we would just have to switch the signs, and then we would read minus 500 as flow from Mozambique to South Africa. We just have to make one decision and stick with it. So one way to do that is we would add two constraints for the 2 different countries. We could do that with a for loop over the countries and have as orientation So as sign, basically the sign would be here the values in the incidence matrix. We would have a +1 if it's South Africa, because we put it on the same like we have it on the same side of the equation as the generation. So we established before we want positive flow to represent incoming flow to South Africa, so it will have the same orientation as the generation. So sign must be positive if we're looking at South Africa, and negative then the other way around. Yeah, it just has to be positive or negative. It has to be positive for one and negative for the other. And then we just look up the load for the other, for the country specifically. And here we just use normal pandas operations to kind of locate all the generators inside the country. So you just look at g.country or g.Mozambique, then it will kind of just list you the subset of the generators that are in that country that fulfill that index. Okay, let's run that, and so we can see we have now this constraint Mozambique, KCL, where we have summed up all the different generators, and then minus the flow that must be equal to the load. And we have the same for South Africa with the different values and a positive value on the flow. Again, objective is exactly the same. We just have one more index, and the sum automatically aggregates across all the indices. So it builds one linear expression here. We add this to the objective, solve it, and then look at the objective value, for example, and the solution. As the solution, we now basically get, because we have two indices, we have this multi-index here to just give you the optimal dispatch decisions of the different countries and the different generators. And you can see, for example, how the hydro capacity was at 1,200, I think, or 1,300. It's not completely used, and that's because we have actually a transmission bottleneck in the flow. So if we look at f.solution, we have flow at 500, so we actually cannot transmit anymore through this transmission line. So that constrains the dispatch of the hydro generator, even though it's super cheap. So this 1,150 is exactly kind of the maximum amount of flow that it can export to South Africa, plus the demand that was 650. So it's not quite at capacity. If we look at the dual prices, it's also quite interesting. So because the transmission line is constrained, we're already importing the maximum of the hydro. The next unit of power generation in South Africa will still come from the gas. So it will still be at 60 euros market clearing price. In Mozambique, it's still 0. We assume 0 for the hydro dispatch. It's because if you have the ability to consume more power locally, there's still a little bit of capacity left of the hydro unit to supply the local demands. So there, the price would be 0. Whether it's shown as -0 or 0 can sometimes be this way or that way. It's kind of it depends on the solver accuracy. Basically, they don't solve to kind of full optimality, but they always have like some numerical tolerance. So it can be that it's slightly negative. Okay, what other dimension can we add, especially for renewable systems where kind of time domain is important, and we want to model storage. We could also model a single bindic zone with several periods. The model looks exactly like we looked at last week, with energy balance and the capacity constraints that are now where the available capacity can be constrained by the capacity factor. And we just want to, there's actually an index T missing here. So we want to sum up across, S and T, the operation across all the different generators and time steps T. So let's reduce again our capacities to South Africa. Look at 3 different time steps. So we just create this time index and build a dummy capacity factor time series where for coal, gas, oil, and hydro we assume full availability. And then for wind we have some time varying capacity factors. That will also just be a data frame with the capacity factors. And the loads now entered as a series with the time index. And of course, nothing speaks against kind of including spatial and temporal domain at the same time. And that's in fact something that we'll do next week. So now our load has just a time index because we reduced everything to South Africa. New model, same method as before, just now calculating the time-dependent upper limits for the generator dispatch. Yeah, I think that's it. For the objective, we can do everything as before. We'll just take G times the marginal cost and sum up everything. Want to minimize that. And then construct the energy balance. And here we maybe have to be careful what we sum up across. So if we, for example, just take g.sum as before, this is not really what we want because it would sum up the generation across all the technologies and across all the time indices. So you'd get kind of maybe something like an annual energy balance or for the whole system scope, but we wouldn't impose kind of hourly balancing or step-by-step balancing of the system. So in this case, it's important to specify if you look at your variables g across what dimension you want to sum up. So you want to sum up across the generators for the different time periods so that you get an expression that sums up the generation for each of the different time steps. And that should match the load, and the load also has this the same time index. Oh. Okay, so one thing, and that already happened the second time, is linopy tries to protect you from adding the same or different constraints under the same name, and will say, okay, the constraint is already assigned to the model, which is in principle good because it means I wasn't careful when constructing the model. If I want to override it, there's an override function, and okay, is it over? I thought there was this function, but okay, maybe not for constraints. Anyway, it's still there. We can check that. So we have this energy balance constraint here, and if we really need to inspect it, we can do n.constraints, energy balance, and constraints. Yeah, and we can check that is actually correct. And whatever we wrote in code, we can check whether that's actually what we want. For small problems, that's of course still feasible. For bigger problems, that's another story. You know the drill. We solve it. Get no complaints. Okay, optimal. We can look at the optimal objective value and access now the solution. Process that a bit. For example, round the values. Turn them into a data frame. Squeeze it, so we turn it into a pandas series because we have squeeze basically means we have a data frame with only one column, so it could just as well be represented as a pandas series, and then we can use the unstack to kind of disentangle the multi-index so that we get a nice data frame where we have time as one index and generators as the other index. So you can see how in time step 3, there's maybe high load, low renewables availability, so that the oil has to step in. You can also look at the duals, and by kind of just running to data frame, we actually get the prices for the different periods. And basically in the 2 periods where the oil is running, it's then setting the price where it's higher. Okay? These are all models where kind of it's designed in a way that you can, in principle, calculate this by hand and follow what the optimization model does. It's a bit of a challenge for big models. So when we run kind of European market analyses, then it can sometimes be a bit messy to really trace why the optimization, why the solution is in the way it is. So you lose, for complex models, you lose some of the traceability, or at least it's a bit more difficult and requires a few more processing steps. Okay, so as the last example, we're staying with a case of single bidding zone and several periods, but we're going to add some storage constraints here as well. We add one store with 6 gigawatt hours of storage, 1 gigawatt of power, an efficiency of 90%, and a very low standing loss. And we can actually just reuse the model that we've used and add a storage unit to the mix. And here, remember, we have 3 basic sizing factors of the and operational decisions or operational variables of a battery storage. That would be kind of the discharging, so the charging, and then the state of charge. And that state of charge is dependent on the charging and the discharging and the state of charge of the previous periods. So it's more of a dependent decision variable. What we do here, okay, all of these values have to be positive. They are limited by the storage power, which for the battery is just the same for charging and discharging. And all of these variables get the time index, and they just get our, just get some names. And then we implement this constraint that you know from last week, where we just kind of implement the relation of the state of charge of the current period to the previous period, and the charging and discharging decisions, including the losses, and also setting the initial state of charge here to 0. So this kind of one small constraint here that we say the battery SOC at time step 0. So if you have series models, that could be a timestamp, for example, is 0. So that's one constraint that we're going to add. And then the next constraint would be for every state of charge from 1 to the last time step. We have the relation 1 minus standing loss times the battery SOC, and we use here this shift function. Shift function of basically offsets the time index by 1. This is basically the Python way of saying t minus 1. And then for every variable that we access, we actually only want kind of the time step 1 onwards, because we already fixed everything for the initial state of charge. And then we just take the efficiency, and again, the efficiency here would be the same for charging and discharging. We just kind of plainly re-implement this constraint. So we get this out, which you can check whether it matches exactly what you would expect from this equation. I would say it does. We have kind of charging and discharging efficiencies, battery SOC of the previous period related to the current period, and linopy will kind of arrange everything that involves decision variables to the left-hand side. So you can see here that it's basically, we wrote it in a way that kind of the state of charge of the previous period, the battery charge and the battery discharge was on the right-hand side, but linopy just normalizes that and moves everything to the left-hand side. So that's where the kind of inverted signs come from. What we need to rewrite is we need to rewrite the energy balance a bit to include the, just a moment. We need to rewrite the energy balance constraint because we now need to factor in, like we did for the transmission, that we have incoming and outgoing flows from different regions. Now we have incoming and outgoing flows from different time periods.
Yeah, for the battery estate.
Yeah.
Doesn't that prevent the battery to be charged or maybe discharged if the initial value is not zero in the very first period, in the period zero?
So basically, it means that in the
first period, which is
so at the
zero,
yes.
can we actually charge or maybe discharge if the initial value is not zero?
So here we have the state of charge at the so we have the state of charge at the end of yeah, it's actually it's slightly wrong here actually that the first period doesn't play a role at all. Yeah. So we only have charging and discharging decisions in steps 1, 2, and 3, not in 0. Yeah, you're right. Good catch. Okay, we need to remove this constraint because we need to account for the incoming and outgoing flows from different time periods. So our energy balance now has the same elements. Oh, what happened now? So it has these elements, loads and generators, but basically we have plus the battery discharge. So that battery discharge would have the same orientation as generation, and the battery charge would have the same orientation as the load. So it would have on the left-hand side a minus sign if the load has a positive sign on the right-hand side. So this we can solve, and now we should actually confirm that the mistake that you discovered. If we look at the well, you have the dispatch that's different than before because now we have a storage operation. We now have some crude values because we have some storage inefficiencies playing a role. Yes. So I think there's a bit of a mistake that in period 1, it doesn't the dispatch decision that we take here, it doesn't end up anywhere. But we have here some charging in period 1, and then some discharging in period 2, and kind of have a bit of discharging left for period 3 that we can see in the state of charge. And could, of course, also look at the duals. Energy, oh, not that. And now the prices will also or can be different. In this case, it's not really different. It's just kind of marginally different. Okay, so I have one job definitely to do. I have to fix the mistake in the tutorial. But that basically concludes how we can formulate basic optimization problems in linopy. It's a very step-by-step process here in this example, where we have to model each of the constraints. Every time we have a different model, we kind of rewrite the constraints. And next week, we're going to look at one higher level of abstraction, where we don't have to write the different constraints, but we just have a formalized way of providing data of standard power system components, like generators, like transmission lines, and we just say what their capacities are, what their other limits are, and then let a tool, in this case Pipeser, handle building of the linopy model in the backend, where we don't necessarily see all the steps of building, and we, of course, don't have to do it ourselves, that then passes to the solver, retrieves the results, and put them in a standardized data format as well. So that's what we're going to do next week. For now, there's a couple of things that you can tweak in the models that we build when working with this notebook. One caveat is that you have to be quite careful because kind of with every example we reinitialize a fresh model with under the same variable name, which is not necessarily good style, but it's compact. So if you want to go back to a previous example, really start from the moment where you initialize a new model, and then you can go through the example step by step. Okay, I would say that concludes the session, and we'll do a floating transition to the consultation hour after a short break.